simultaneously been working for the ECMWF as a software engineer for the last 8 years. Nicolau, in addition, also spent 3 weeks as a part of the CISL Visitors Program last month, visiting here in CISL, performing some I/O kind of benchmarking performance, essentially using our credits ML framework. And on kind of different data formats and architectures and storage techniques on our NCAR HPC. So with that, I think he's going to talk a little bit about that and a little bit about the general data workflow in ECMWF. And with that, I will pass it off. It's all yours, Nicolau.
Great, thanks very much. Let me start by saying thanks for this opportunity to present here in this CISL seminar series. Thanks very much as well for hosting me last month. Thanks in particular to the Miles Credit team and Charlie for hosting me. I'm Nicolau. Charlie has already introduced me. And today I will talk about the data handling approaches at ECMWF. This presentation will have 3 main parts. The first part will be introduction of what we do operationally at ECMWF, how we handle the operational data pipelines. Then I will talk a bit about novel data handling and data access approaches we are working on or we have developed. And finally, I'll quickly review the results obtained during the visit last month. ECMWF stands for European Center for Medium-Range Weather Forecasts. It's a European intergovernmental organization which was established more than 50 years ago. We have several duties, but there are 3 more prominent duties and maybe more relevant to this talk. We are an operational service. We are committed to deliver global weather forecasts to our member and cooperating states. We need to do that 4 times a day under strict deadlines. We also maintain a large meteorological data archive, also known as MARS. It is the largest meteorological data archive in the world, and it currently holds more than 600 petabytes of meteorological data. And we are also a research institution continuously trying to push the boundaries of what can be done in the field of weather forecasting, be it with physics-based model or machine learning models. We also produce data sets of relevance to the community, but that's maybe not the main focus today. So the most relevant activity we do for this presentation is probably the operational weather forecasting. So I'll walk you through what one of those operational pipelines looks like. We run our models, IFS for physics-based, with the physics-based model. We also have AIFS, the machine learning-based model. We run those on our HPC. And these models produce plenty of meteorological data, which we store into a parallel file system. Currently, we have a Lustre file system as HPC storage. Most of these data are 2-dimensional fields stored in GRIP format. Then we also run product generation tasks, which generate derived products that we are also committed to deliver to the member states. And once everything is ready, then the dissemination software stack comes into play, ensuring that those products are delivered efficiently and smoothly to the member states. Also, we regularly migrate some of the data from HPC storage onto tape archive into MARS, so that we can release some of the space in HPC storage because the capacity there is relatively limited. But that MARS is not part of the operational workflow. What we do operationally is running the model, generating the products, and delivering to member states. And there are strict time constraints to do that. We have to, since we start the model until we deliver the product, we have 1 hour. Currently, we produce around 120 terabytes of data during one operational pipeline. And the projection is that by end of 2027, we will be producing around 250 terabytes due to resolution increases in a number of dimensions. So, due to the nature of our activities, there are a number of data handling challenges. In first place, we have a wide range of user needs. We have both internal and external users. For example, an external user who requires to have the forecast for tomorrow as soon as possible. Another research user who requires the precipitation data for London for a long time range. Another user who requires data for a forecast for a specific country for a date in the past. And internally, we have, for example, research users who require to introduce new experiments into the data archive or require their data to be stored in HPC storage during 5 days. In the end, we have a wide range of user needs that need to be catered for. Also, these activities result in vast amounts of data for many different work streams and many different parameters. Uh, and this also poses a data governance challenge. We need to uh, have a good, solid strategy for how these data are stored in terms of format and in terms of conventions. And also we need some mechanisms for those data to be actually useful. It's very good to have tons of data, but if there are no mechanisms to make good use of those data, these become useless. So there need to be mechanisms to make those data findable and usable. Also, as I've mentioned, we operate under strict operational deadlines, and this implies that during these operational windows, we need to run both data producers and data consumers. And this means that we have strong contention on the storage system, and our storage system needs to be able to handle this contention. Also, there are planned resolution increases in several dimensions. We may increase number of ensemble members, we may increase spatial resolution, and this poses a challenge not only at the storage level, but also at the computer system level overall. Both the computer capability and the network capability need to handle those increases. Also, lately, we are seeing the machine learning models gaining traction, and these operate differently. These have different storage access patterns. They are more bursty. They produce lots of terabytes of data in a few seconds. And this is a new access pattern. This is a new use case that the storage system needs to deal with while still being able to handle the traditional access patterns. So, what is our approach to those challenges? So, I would say there is a fundamental approach. It's threefold. Um, um, these are, I will present now three very simple ideas, but these are very powerful, and these establish the foundation for all the rest of operational components to build upon. So the first key idea is that we have an object-based approach. Uh, our data is divided into many small components, and each of those components, we also call them messages, are self-describing. They have headers and they describe themselves in a compact way, not to use too much storage space. This means also that our data handling approach has a granularity of 2D fields. For example, we have at the moment three different message formats: buffer, ODB, and grip. And most of the data we produce is 2D fields stored in grip format, which means that the granularity of our data is at the 2D field level. Also, we have a semantic language. We call it the Mars language, which allows us to uniquely and meaningfully identify every single data granule, every single data message. And this language is used across all our operational components and all other downstream data handling components. And this allows to build an ecosystem of applications which all talk in the same language and can interact well and efficiently. The third key idea is that we maintain an index of the full data domain, and this is maybe in contrast with what other institutions do. Uh, Usually, other climate and weather research institutions maintain files with several weather fields in those files, and then they use the file names to have an idea of what's in those files. On the other hand, we use this separate index independently of the file system, which allows us to locate every data granule individually. You can see at the top right an example of the Mars language identifying a given weather field, and at the bottom you can see a representation of the index that we maintain separately of the file system. So these are three rather simple ideas, but very powerful ones, which establish the foundation for us then to build all the other operational components. There are many data handling components and data processing and data access components, but I'll talk briefly about two of them because these are the ones that are mostly involved in the operational pipelines. One is multi-IO and the other is FDB. Starting by multi-IO. Multi-IO is a software stack that we deploy on a designated set of nodes in the HPC. There's a little representation here at the bottom. You can see at the very left a bunch of model processes that are running on the HPC. And then we also have a designated set of nodes running IO servers, that is multi-IO running here. And basically, those IO servers receive IO from the model processes such that we only have a limited set of processes interacting with the storage system. Otherwise, if we had all model processes performing IO against the storage system, we could overload the storage system and potentially exhaust resources on the storage system server side. So yeah, the main function of multi-IO is funneling IO. It is also referred to as IO forwarding. And it also does some routing activity. We have a number of storage systems with different storage media of different capability. So someone needs to decide where the different data sets are routed to. So multi-IO is doing some of that. Also recently, we have developed capability for multi-IO to perform on-the-fly post-processing, generating some of the derived products on the fly before data is archived into storage, so that then we avoid some of the post-processing later on. But still, we have anyway post-processing later on because not everything can be done on the IO servers. The other relevant operational component is FDB. It's again another software stack, which basically abstracts away the file system, the storage system behind the Mars language, such that operational applications can then archive and retrieve weather fields from the file system with a very simple API, which is represented here in the figure at the top right. We see an example of an application which has binary data for a weather field in memory, and it calls the FDB write API, providing a Mars compliant identifier, and that field is then archived, is written behind the scenes into the Lustre file system in a way that is performant and in a way that is consistent. And also an index will be populated internally by FDB so that we can maintain that overall index that I was mentioning earlier. And then later on, other applications can then call the FDB read API, providing the same Mars identifier for that weather field, and the data for that field is returned. So in short, the FDB simplifies the IO for the operational components. We've seen now a very brief summary of what we use operationally. And now I'm going to the second section of the presentation, and where I'll show three novel uh, data storage and access approaches that we have been working on. The first one is native object stores. So as I have mentioned, we are currently using POSIX file systems operationally. We are using a Lustre distributed file system, but there is a concern that POSIX file systems may not scale for future resolution increases. And there are a number of reasons for that, which I have listed here. In first place, POSIX file systems can be quite metadata prescriptive. You have to maintain, well, the file system maintains not only the file name, but also creation date, modify date, access permissions, ownership. And that's a lot of metadata to maintain for every file. And for very metadata intensive, for applications using many files, this can be a lot of metadata. Also, the kernel, both on the client side and on the storage server side, the kernel is involved, needs to maintain data structures in memory to manage those files. And not only this means that there is an overhead there because the kernel needs to maintain those data structures, but also we need to switch context between user space and kernel space, at least on the client side. And this can also become a bottleneck at extreme scale. Also, POSIX file systems build on top of the block device API, meaning that if an application needs to access a specific byte or a small byte range, an entire block will be fetched from storage. And for certain applications, this can really penalize performance, and lots more of data than the required will be actually retrieved. Also, distributed file systems usually implement client-side caching to improve read performance. So if an application is reading the same data several times, it won't fetch the data every time from storage, but it will pick it from the cache. And because there can be caches on multiple clients and also on the servers, there need to be mechanisms to ensure coherency across all those caches. And what file systems do is they resolve this issue with a distributed locking mechanism, but that implies that every time a client wants to do an I/O operation, it will need to negotiate a lock with this centralized lock server. And that can result in lots of communication overheads, and that can also bottleneck. Also, some file systems like Lustre have a designated set of server nodes which are devoted to serving metadata. And for very metadata intensive applications, that can bottleneck. So at ECMWF, these things worried us. So a few years ago, that is 5 years ago, we saw there were object storage solutions proliferating in the space. And particularly there was one, which is DAOS. At the time, it was being developed by Intel. It is now part of the Linux Foundation. It is being maintained by HPE, but at the time it was Intel developing it. And DAOS was designed for high performance and provided solutions to all of these issues. It DAOS provides objects. It is an object store. Instead of files, it provides objects. Those objects have minimal metadata associated, and then it is up to the application to create metadata as desired. It operates fully user space, not involving the kernel. So we remove another potential bottleneck there. It is fully byte addressable. DAOS does not support hard HDDs. It only supports NVMe drives and also persistent memory, although it is no longer an option in the market. But thanks to that, it means it is fully byte addressable. So you no longer have those overheads of retrieving full blocks. It does not implement client-side caching, so there doesn't need to be distributed locking, and therefore we remove another potential bottleneck. And the metadata serving is fully distributed across server nodes. So after a preliminary assessment, which is documented in a paper from 2022, if I remember correctly, we did a preliminary assessment. It was positive. So we implemented a new backend for FDB to operate on this new object store on DAOS. We also saw that Ceph was a relevant object storage in the domain. So we also decided to implement backends to support operation on Ceph. And here at the bottom of this slide, I'm representing the different concepts and APIs that DAOs and Ceph or Rados have to offer. Basically, they provide pools which act as a form of storage partitioning. And then within those pools, one can create namespaces or containers, where you can, isolate the namespace in case any other application uses the same object names. And then within those namespaces, one can create objects. And usually object stores provide two types of objects. One is the regular objects where you can write binary data blocks. And the other are key values, which are similar to dictionaries in Python, where you can associate keys of arbitrary length to values of arbitrary length. And these key values are consistent at all times. And this is a very useful feature to implement functionalities such as the FDB backends, where an index needs to be created and maintained. So yes, we developed those backends, and then we did some benchmarking experiments. And I'll take a bit of time to explain those experiments. Basically, we got access to Google Cloud, a number of virtual machines in Google Cloud, which had NVMe attached, specifically 24 virtual machines with NVMe. And then we also got access to another bunch of VMs to be used as clients. So what we did is we deployed DAOs, then Ceph, and then Lustre separately, one after the other, and removing the previous when deploying the next one. We deployed the three storage systems on those VMs with NVMe, and we ran a benchmark which consisted of long series of FDB archive and FDB read calls to hammer the system and test the performance when exercised from multiple parallel streams. And so here I'm representing the results of those experiments. On the left side, we see write bandwidths. On the right side, we see read bandwidths. On the x-axis, we see the number of VMs used to deploy the different storage systems, ranging from 1 up to 24. These VMs had NVMe again. And then on the different colors, we see the bandwidth results for the benchmark runs against the different storage systems. In blue, we see the results for DAOs. We saw that it scaled roughly linearly, both for write and for read. And that was a very good result, an encouraging one. In orange, we see the results for Lustre, again, deployed on the exact same hardware. And we saw that for write, it did relatively well, coming close to DAOs, but beyond 16 server nodes, it plateaued. So this plateauing, we did some detailed profiling, and we saw that it was just Lustre struggling to do some small writes to maintain the index up to date. So really, there was nothing we could do or there was not an obvious way to improve that. So we were quite certain in saying that DAOs could provide superior performance, at least for our workload, and superior scalability, which is more important. On the read side, we see that Lustre in orange drifts away from the DAO's performance significantly. And at the time, we did not fully understand that result, but a few weeks after, we realized there were inefficiencies in the FDB code to operate on POSIX, which were then addressed. Probably if we rerun those experiments today, we would see this orange curve coming closer to the DAO's one. Then in green, we see the results for Ceph. For write, we see that it did consistently worse than the rest. And then beyond 16 server nodes, it plateaued. This consistent inferior performance, after some in-detail profiling, we saw was probably due to the fact that Ceph was configured to persist the key values directly on NVMe, whereas DAOs was configured to persist the key values on DRAM. So this was maybe not fair. DAOs should not have been configured to store key values on DRAM, but at the time that was the only option possible. A bit later on, they developed the functionality to persist directly on NVMe. So these experiments could be rerun and made totally fair. But yeah, so we expect that if we rerun with Ceph using DRAM for the key values, that would go slightly higher. But the plateauing beyond 16 server nodes, there was no obvious way to improve that. And we think again that DAOs did provide superior performance for our use case. Then on the read side, we saw Ceph did actually quite well, coming very close to DAOs, although it plateaued again beyond 16 server nodes for unresolvable reasons. So yeah, Ceph was very good, but at larger scales, maybe DAOs was the better option. The conclusions that we drew from these object storage experiments were that DAOs seemed to show better scalability for our workloads. There are still things that need to be confirmed. We need to test DAOs without using DRAM, confirm that it does not massively affect the performance. We don't expect performance to be affected massively because our workloads are not very extremely metadata intensive. So that shouldn't be a problem. And also these experiments need to be run at larger scales. For an operational system like the one required for ECMWF, one usually has on the order of hundreds of nodes for storage servers. So we did our experiments only up to 24 nodes. So maybe at larger scales, these results do not hold. We concluded that Ceph can do well for read, and that can be suitable, for example, if one needs to implement a data service. We saw that object stores can enable new I/O patterns at scale. For example, one can do small I/O operations, lots of metadata operations and key value operations with object stores, and that was not possible before with POSIX file systems. So in the end, object stores provide more flexibility to perform I/O as desired. And this was very visible in the code for our FDB backends. The FDB backend for the object stores was rather simple compared to the code for the POSIX backends, which required lots more of mechanisms to build the index particularly and to keep things consistent at all times. One caveat is that object storage, if you want to obtain the best performance, you need to use the native APIs, and that requires a non-negligible porting effort. All object stores nowadays provide POSIX interfaces such that you can use them through POSIX files and directories, but they have downsides sometimes. For example, the DAO's POSIX interface provides very good performance, almost native performance, but it is not fully POSIX compliant, which means that at ECMWF we cannot yet adopt it for operational workloads because there are operational components that do require full POSIX compliance. Right, moving on to the next novel data handling approach that we are considering. This is particularly a data access approach. It is called Polytope. So, as I've mentioned previously, we store the data in GRIP format. Well, large part of the data we store in GRIP format. And due to that, our tooling requires to retrieve full fields from storage at the moment. And meaning that if an application needs to do granular access of specific regions of the Earth's surface, there will be overheads, there will be a read amplification. And so Polytope provides granular access, efficient granular access for grip data in the FDB. And this can have a dramatic performance effect for certain applications. Polytope is composed of three components. The most basic component is a library called GripJump, which enables subfield level access to grip data. And those data can be either stored in FDB or outside FDB. Using this library, one can access specific byte ranges of those grip data. Then there is another component, which is a rich API for specifying subsets for slicing the data domain. And we have a few examples represented here at the bottom. We have an API to provide, to specify polygons for the Earth surface, to extract polygons over time steps. We can also do complex things like spatiotemporal trajectories following a flight path, for example, where you have a polygon that changes position or shape over time. And then we also have the typical use case of requiring to extract data for a specific grid location. And this is very useful, for example, for forecast verification tasks, where one has the location for an observational station, and you can provide that location to Polytope, and it will find the nearest location in the forecast data and extract the time series for that location. And finally, we have the last component of Polytope, which is a software layer to expose this feature extraction API over the network and expose FDB data through that API. And that can be very useful, for example, for cloud environments. This is a very simple example of what one can do with Polytope. For example, imagine an application which needs to analyze data for Spain, France, and Italy. If that application were to use the grid fields without Polytope, it would need to fetch 105 megabytes from storage. But as soon as it uses Polytope and provides the specification of the boundaries of the region of interest, then the data fetched from storage goes down to 4.8 megabytes. And there are other use cases, typical use cases, where this percentage of reduction is even more impressive. For example, when extracting time series over very large climate data sets, the percentage of reduction can go up to 99.999, several nines. Right, and now moving on to the last data access approach I want to present today, which is called Z3FDB. And the aim of this software layer is to expose data in the FDB as ZAR arrays. I have prepared an animation here which shows what can be done with Z3FDB. Basically, a user application requires to work with a specific data set. So the application can supply Z3FDB with a specification of this data domain with a Mars compliant specification, and then specify as well the desired shape that those data should be presented in and the chunking configuration desired for that data set. Z3FDB will fetch the required metadata from FDB and will build a lazy view in memory which does not yet contain the actual data. It is just a logical view of the data set and returns it to the user. And then the user can interrogate this lazy view with data queries. And then Z3FDB will go back to FDB and retrieve the actual data chunks to be returned as a ZAR array to the user or application. Yes, so this approach is interesting because, as I've mentioned before, FDB stores all the data as 2D fields in the grip format. and one can create logical views with several different chunking configurations over that data, and with that the user can adjust the read amplification that will result. As you know, when using ZAR datasets, the data is chunked, and if you hit a single byte from a chunk, you will end up retrieving the entire chunk from storage. So with this approach here, one can build logical views with different chunking configuration such that the data retrieved is only the bare minimum required. This approach is expected to have an overhead over native ZAR access. Of course, when you create a ZAR dataset for your application, you create your chunks in the optimal configuration. Those chunks are compressed, and this is very efficient. Uh, um, and in this Z3FDB approach, we have all the data granules stored in GRIB and compressed independently. So there will be an overhead for extracting and decompressing every single data granule separately. But it has the potential to provide balanced access cost for a wide range of access patterns. And that's where we see the potential for Z3FDB. Right, now moving on to the last part of this presentation. This is a picture I took last month during my visit, a few days before it snowed. During that visit, I started by running a few IOR experiments. IOR is a very popular IO benchmark to test the IO performance of storage systems. And I run this benchmark on a Casper node with A100 GPUs. GPUs do not matter here, it's just for you to know which type of node I was using. I run IOR on this node against the different storage systems available. The first one was Scratch, which is Lustre based. The second one was Campaign, which is GPFS based. It's a large capacity one, lower performance than Lustre. And the other one was Boreas, which is also GPFS based, but it is exposed through an S3 interface. And this is an object storage interface. This Boreas service was backed by a small GPFS instance, separate from the Campaign GPFS instance. The Boreas GPFS instance only had 2 server nodes, if I remember correctly. And so here we see the results I obtained. On the left side, again, write bandwidths. On the right side, read bandwidths. On the x-axis, we see number of IOR processes run on that Casper node. And on the different colors, we see the results for the different storage systems. We can start by Lustre in green. We saw that we could reach about 25 gigabytes per second for write, and relatively large process counts were required to achieve that optimal performance from 96 onwards. These nodes had actually 128 physical cores, so I was maybe hitting the maximum that one could run there. For read, we saw that Lustre could provide much higher bandwidths. Actually, it goes off the chart, but with 128 IOR processes, I could reach up to, I think, 90 gigabytes per second. So yeah, this demonstrated that effectively Lustre can provide much higher performance than the rest, at least when running from a single node. Then looking at the orange curves for Campaign, we see that we could reach around 17 or 18 gigabytes per second for write, and around 15 gigabytes per second for read. And here GPFS was not so sensitive to process counts. With relatively low process counts, one could reach the best performance already, which is around 8 to 16 parallel processes. And finally, the one that was of most interest here is Boreas. Again, we tested Boreas with IOR. For write, we reached up to 8 gigabytes per second, which is significantly lower than Campaign. But here, this, I think it was limited by storage resources on the server side. uh, potentially with a larger Boreas instance, we would have had similar bandwidths as campaign here. And for read, we reached up to, let me check, up to 18 gigabytes per second. And this was a positive result. It was even exceeding the GPFS bandwidths. Um, so yeah, very encouraging, because we didn't expect S3 to provide such good performance, because it is using the HTTP protocol, even HTTPS for security, and that can have lots of overhead. This was a relatively surprising result. It's worth noting that Boreas was more sensitive to process count. One had to use large process counts to obtain optimal performance. And this is probably because Boreas, due to these HTTPS overheads, is a high latency system. And therefore, in order to hide this latency, one needs to have more parallel streams. Also worth mentioning that to achieve good performance on Boreas, relatively large objects had to be used. We first tried with 1 megabyte objects, but this killed performance. We got 10 times less performance. It is only when we started using 100 megabyte objects that the performance was started to be decent. Now, after testing with IOR, I was ready to test with real world applications like credit. But before doing so, it was really necessary to find a proper tool for profiling those runs, to get some measurements and then do proper analysis of what happened. There were two things that we were particularly interested in. The first one was the amount of bytes written and read from storage. Since we have chunking in ML applications, they use Xarray and Dask and ZAR, and there are a couple layers of chunking there, and this can cause lots of read amplification. So we were really interested in measuring how much data was really fetched from storage. The other thing we really wanted to know is what portion of the total runtime was actually spent on I/O. And we tried a number of different tools like S-Trace, like the Grafana dashboard, like NVIDIA Insight, and a few others. But eventually, the one that worked best was Darshan. It was suitable to measure those things for complex applications, and it did not really require the applications to be MPI based. And then this is the final slides result. Um, this is a summary of the results we got from running credit on top of a number of storage formats. We got a data set, ERA 5 data set for a specific year, 2021, if I remember correctly, daily 6 hourly data for 2021. And we run credit training on top of those data. The credit run was configured with 3 epochs and 25 batches per epoch. And it was configured in all these experiments here, it was configured with no prefetching, no pre-blocks, and no parallelism for the data loader. So it was the simplest case possible. But this already allowed us to get some insight. The first experiment we did is running on the data in ZAR format with chunks of size 10 along the time dimension. It is worth noting that credit accesses different time steps randomly, not contiguous time steps. Therefore, having time chunks of 10 should result in lots of read amplification. And that's actually what we saw. It is shown here in the second column. For the first row, we saw 107 gigabytes were retrieved from storage, when actually, as shown at the bottom, the size of the data on disk was 7 gigabytes. So this means there was a read amplification factor of 15, nearly 15. The next experiment was running the same credit run on the same data set, but configured with time chunks of 1. And here we saw that the amount of bytes read from storage went down dramatically, as expected. But still, there was some read amplification, right? Ideally, we would want to see 7 gigabytes here, but we saw 19. So there is some read amplification. And my guess at the moment is that this is due to Dask chunking configuration. It is important to notice that one can have chunking at the ZAR level, but usually ML applications, they use X-array and Dask for distributed operation on X-array objects. And Dask has another layer of chunking, which, if not configured properly, can also trigger read amplification. And I'm pretty sure that's what happened here, because during some of the runs, I could see the Dask chunking configuration being reported, and I saw it had time chunks of 2. So probably that's what was happening here. The I/O time went down significantly from the previous run, of course. Then the next experiment was running the same credit application on top of the data re-archived into FDB in grid format and exposed via the Z3 FDB layer that I've just talked about. In this case, the data on disk, as shown at the bottom, was 12 gigabytes, and the application here was retrieving 24 gigabytes. And that was, again, probably due to the factor, due to the Dask chunking. So we were retrieving 2 times the required data. The I/O time went up relative to the ZAR experiment with the corrected chunking. And yeah, this was a bit disappointing, but also somewhat expected, right? Because as we have mentioned before, FDB stores the data in small granules, and then the extraction and the decompression needs to happen for every granule individually. And here we had a single data retrieval process, and probably that process was part of the time working on I/O and part of the time working on decompression. But still, it raised the question: is there anything we can improve at the Z3 FDB layer to to bring down this I/O time? This note was taken, and we will investigate. But still, it is worth noting that Z3 FDB is designed to provide uniform access cost for a wide range of access patterns, not necessarily the one being used here. The fourth experiment was running again the same credit application on top of NetCDF data. The data in this case was 70 gigabytes in storage, and the application was again retrieving 2 times that amount of data. Again, probably due to the Dask chunking. And finally, another experiment was Kerchunk is a library which allows to create virtual ZAR datasets pointing to already existing GRIB or NetCDF datasets. And so we created a Kerchunk dataset pointing to the same test data, and we run credit on top of that. And in this case, the result was, I have to admit, was a bit surprising, because the amount of data read went up, and I asked myself, how can it go up if it's the same data? We just have logical pointers to those data. It should not go up unless it messes up with the chunking configuration. But what's more surprising is that the I/O time went down relative to direct NetCDF. And these two results in combination are just very surprising and not well understood yet. So yeah, there more investigation should follow to properly understand that and see how to really apply this approach to the real credit runs. That was all done in the visit. Conclusions from the visit were that the performance of the different storage systems at NCAR was better understood, and particularly we saw that Boreas can do well for read as long as you use sufficient parallel streams and as long as you use large enough objects. Also, another high-level conclusion is that we managed to establish a methodology to analyze the performance impact of those different storage formats for ML applications and for credit in particular. And this allows us to do more experiments in the future if needed. Out of the data formats, ZAR was the most efficient in terms of data movement. It compressed the chunks very well and it reduced the I/O. But chunking is important. It needs to be done properly both at the ZAR layer and at the Dask layer. Z3FDB was actually also relatively efficient in terms of data movement, but the I/O time was unfortunately worse, and there may be room for improvement there in the Z3FDB layer, but this needs investigation. Um, and yeah, these results are very preliminary. For example, the Kerr-Chunk experiments are really not conclusive, do not inform us on how to proceed in the future. So more experiments should follow. And now, reaching to the end of this presentation, I think the overall conclusions of this talk are that, well, at ECMWF, we have a well-established approach for data handling, which revolves around semantic metadata, revolves around an index of the whole data domain, and it is object-based. And these simple ideas are very powerful and support an ecosystem of data handling components to be developed on top of. Also, we have seen that native object stores like DAOs are promising. They can provide superior scalability for our workflows. And object storage interfaces like Boreas are also promising. They can provide good read performance. And these object storage approaches play well with our infrastructure at ECMWF, which is already kind of object-based. We have seen Polytope, which is a novel interface for granular access to ECMWF's data, and it can have a massive impact on I/O performance. And we have seen that there is work ongoing to provide ZAR access to ECMWF's data for ML applications. And that's everything. Let me wrap this up by saying that if there is interest in sharing similar experiences or you would like to ask on any of the presented components, please do reach out to the development section at ECMWF. And that's all. Thank you very much for your attention.
Sam, do you want to moderate questions?
Yeah.
Just noting that the volume is a bit low on the room microphone.
So any questions in the room to start with?
Hi, Nicolau. So great to see all the results come together. Do you mind going back to the table that you had at the end?
This one, I suppose?
Yeah, that one. So the size that's listed at the bottom, is that for one time or for the time pair? So like when you're training the model, you have t and then t plus 1, or in this case, I think 6 hours ahead. So is it like is the 7, 12, 17 for the one time or for the pair?
It is this first, happy to see you. Thank you for the time we shared there. I'm really happy to see you. These numbers are the total amount of data that the credit run is supposed to read from the entire data set. It's not a single time step. It's not the entire data set. It's the number of epochs multiplied by the number of, by the byte size multiplied by the size in megabytes or gigabytes of every sample.
I see. Okay, thanks.
Thank you.
Any other questions in the room?
Thanks so much, Nicolau. I have a question, I guess, about Polytope, because I know that we didn't have time to really investigate that here, but what is the output format of Polytope essentially look like, especially if you have like non-contiguous grids? Like, does it come out as is this user configured, or is it just like a JSON file essentially, or does it kind of depend on whether it's a time series point versus a region. I'm just curious.
Exactly. You said it right now. So when your request results in 2D fields, it is returned in grep format. But if your request is more complex and complex shapes or time series need to be returned, then these are returned in OGC standard formats. And I don't remember the actual name of the standard. Sorry, I don't remember the name, but it is an OGC standard. And there are actually two standards that you can get the data returned in. One is OGC EDR, I think, but that's a more complex one. There's another one that Polytope uses by default, but I don't remember the name, sorry.
I see. No, thanks so much.
Okay, and just a reminder for those that are streaming, if you want to submit questions, you can click the tab to go to Slido and submit a question there. Are there any other questions in the room here? Okay, maybe we'll just give it one more minute in case someone does have a question that is streaming and didn't know they could submit their questions. Okay, we have one on the Zoom call. And you should be unmuted, so you can go ahead and speak for your question.
Hey, thank you for the great presentation. I really like particularly the end comparison between like ZAR and Kerchunk. And I was wondering, for the Kerchunk part, did you generate a Kerchunk reference file based on what you need to read? Or it's a aggregation of the file that you need to read?
The Kerchunk is a library which I use to produce a virtual ZAR data set, both in Parquet and in JSON formats, both resulted in the same performance. And these virtual data sets contained pointers to the entire netCDF dataset.
Right.
The chunking of that virtual dataset is inherited from the netCDF data. Given the netCDF data had an unlimited time dimension, then the final virtual dataset contained a chunk for every time step over that unlimited dimension.
Right. So my question, I guess, is the inflation that you mentioned about the read
yes.
data size, would that also count the reference file data size?
No, I think I actually measured the size of the virtual references on disk, and it was around 1 megabyte. So by no means this large amount of data read from storage can be due to the virtual references. It must be data being reread or data read that was not actually needed.
Yeah, thanks.
We do have one question online. Sorry if I butcher these acronyms. Can you talk about what requires POSIX at ECMWF, and what are the deal breakers for that software using the object storage?
So we have a main use case during our operational runs, which is the field and meteorological data input and output, and all of that goes through FDB. So with the DAO's backends, we are good, but there are still a number of other components, applications doing data processing, doing checks of what's available in the file system, which actually require POSIX compliance, rely on, for example, atomicity of the make-dir operation, and things like that require maybe advisory logs, which is a thing that is not currently supported by the DAO's POSIX interface. And it is just not viable at the moment to port all of these components to a new storage system that is not POSIX compliant. It just not only difficult, but also dangerous, because it can potentially break our operational workflow, and then we would fail to deliver what we are meant to deliver during that time critical window. So that's why we are very afraid of doing that.
All right, and with that, we are at time. So thanks again to our speaker today for the wonderful talk. And thanks everyone for joining the May CISL seminar. Next month, we have one planned for June 25th and potentially another in the works. So keep an eye out for notification about that. Thanks, everyone.
Thanks very much. Bye-bye.